Hi, my name is Pablo Galindo.
And my name is Łukasz.
And this is the Core.py podcast, a new podcast where we discuss the internals of CPython or adventures in making a new version of your favorite programming language. Today, we will be talking about PEP 703, which is basically this PEP that removes the global interpreted lock. If you don't know what it is, don't worry, we will go very deep into the topic. And we will talk about everything that you need to know about the most exciting Python change in a long time. Even if you pretend to use the thing or you want to maintain the thing, which is two different things, as many people will soon find out.
Right. Let's maybe start with the current state of things. So how does Python work today and why is this a problem?
The key point here is basically that CPython uses a way to manage memory called reference counting. The whole schema is more complicated because then there is like cycle GC and whatnot. But the basic idea here is that reference counting is the main schema to manage memory. And the idea is that every object knows how many people are using it. So if I have a list and then I have two variables pointing to my list, then the reference count of the list is 2. And the whole thing is that when reference count reaches 0, we know that nobody is using the object and CPython can deallocate the object, right?
Right.
And then, you can, if you are one of these smart ass people, you can say, well, what happens if I have like one object that points to another object and then that another object points to the first one and nobody points to any of these two. And then you have what is called a reference cycle. And then we have our, this whole different thing called the cycle GC that is in charge of, detecting these reference cycles and removing them, which, is a bit more complicated and we are not going to go into detail. Right.
Okay, so this memory management scheme is very useful for the users of Python since you don't have to actually think about memory management yourself. And in fact, even though it is dynamic, it is very predictable. Like when you leave a block where an object was created and it's not actually given anywhere else, Python can rather reliably know that, okay, now this is the time to decrease the reference. And if the reference reaches 0, we can free memory. So this is tremendously useful and also not extremely complicated to get right thanks to one global interpreter lock that we have that is used for all sorts of operations to make sure the internals of the interpreter stay correct when you are dealing with multiple threads of execution. So for example, all this reference count in creffing and decreffing is something that we need to make sure is atomic and is not going to be broken by another thread trying to do the same thing at the very exact same time. So, with the reference counting, for example, incrementing only once instead of twice. But the global interpreter lock is used for many other things. Most importantly, to protect internal memory representations of PyObjects. So any kind of object that you have in Python is going to have its header with a bunch of internal information there. And internal data structures like dictionaries, like lists and whatnot. When you're adding or removing an element from them, any sort of mutation, we will use the global interpreter lock to ensure that it is still atomically represented with some valid state. So you're not going to have a situation where an object is in the process of being added to a list, but we're not actually quite done with that yet and you're reading an invalid list. So we actually have the GIL as this one central way to synchronize those operations. And that makes stuff easy for us to reason about, but it actually limits what you can do when you want to run threads. But Python does have the threading module, right? So why even bother with the threading module if we have this global interpreter lock that causes things to never run in parallel? Well, never is a strong word. In fact, we have plenty of opportunities to free the global interpreter lock from the current thread when we know that the current action executed in that thread is not going to touch Python. So if you're doing some computation straight on bytes, I don't know, converting an MP3 or doing some operations on like in-memory arrays that don't actually have anything to do with PyObjects, you can, for a while, free the global interpreter lock. If you're waiting for external I/O for a network, you can do the same thing. So threads are, to some extent, usable in Python even today, but the most popular thing that they would be used for, which is user code parallelism, is not at this point enabled. It's not possible with the global interpret lock as it is now.
Right. And there is a lot of hunger for the idea of being able to actually run, parallel computations in Python. Even if for a long time we have said, well, you have this model when, things are maybe not parallel, but, most of the cases are kind of fine, especially for I/O. So you can still run your HTTP server kind of okay with Python because, most of the threads will be waiting for data on sockets.
Right.
There is still cases when this is not enough. And in the modern world, CPUs are not like faster and faster and faster in a single core. We don't have like CPUs of 25 gigahertz, right?
Yeah.
What we have is a lot of cores. And even these days, we have a stupid amount of core in some of these CPUs. I think one of these Ryzen has now 90 something cores, which is bananas.
Yes, the new Threadrippers, right?
Right. Yeah. It's only $2,000 of CPU. So now they are competing to see if the GPUs are more expensive than the CPUs. We will see who wins.
Right. Even in your phone, you're going to have like 10 cores, right? So like this kind of world with multiple cores is not something that is just relegated to high-end computing. Like everybody has a multi-core computer in their pocket now.
Exactly. So, for instance, there is a lot of cases when still this is a huge difference. For instance, if you happen to run, let's say, numeric code using Python objects, even if you're using NumPy, yes, a lot of the operations happen in C, but like still there is a lot of the stuff that still happens in Python. For instance, every time, and this is something that a lot of people don't realize, every time you convert some of the C objects to Python objects, you need the GIL, and therefore, if you have a heavy array, and then you need to transform this into a lot of Python objects, then you need the GIL for that. And if you have multiple threads doing the same thing, then only one thread at a time can do the conversion, apart from the operations and so. So that's one of the cases. The other case is basically the idea of sharing objects between these threads without having to serialize and deserialize these objects. For instance, recently in Python 3.12, we have multiple interpreters. This is a way to circumvent the GIL limitations. And the idea is that you can have like several copies of Python in the same process. But the problem is that you can still have like one list and send it to another copy of Python. You need to basically copy it. So every copy of Python has its own version of the list. There is no way to have, let's say, a big cache that is shared between all these copies of Python and use for lookups. You need a whole copy, so you still need to duplicate memory and pay for the serialization and deserialization, at least for now. There is things that we are trying to do to avoid this, but if we didn't have a GIL, you could literally share this thing in a safe way without having to worry about it.
Yeah, exactly right. Since we had ways to overcome the limitation of the global interpreter lock in the past. Multiprocessing was one, and you could use it kind of in an elegant way from async IO with the process pool executor and so on and so on. So as long as the amount of data that you needed to share between your kind of orchestrator process and the worker processes wasn't huge, this usually wasn't a big deal. But as soon as the amount of data shared between the workers and the orchestrator were large, you would see that in fact like all this multiprocessing business is just kind of circumvented, is limited by the time spent serializing your memory objects into something that another process can now access and read, and then doing the same the other way around when you made the computation you wanted to do. So being able to share data without serialization is a very important use case for this.
Right. So this is, I hope we convinced you that this is actually quite important, and a lot of people want this from the, the numeric world, from the server world. So this serves everyone, right? So why we don't have it, Łukasz? Maybe it's interesting to see like the story of this change, in the sense that a lot of people actually have tried to fight this battle, and unfortunately we have not succeeded. So maybe it's good to quickly go through all the current attempts to remove the GIL and briefly discuss why they fail.
Right. So in fact, we could have had it a long time back, even in 1999, at the time of Python 1.6, Greg Stein did actually remove the GIL successfully. The only problem with that was replacing one very coarse lock with many small locks for making the reference counting operations still valid, made the performance of the interpreter way worse. And this is why this patch was eventually abandoned, since the changes required to maybe overcome this limitation were increasingly of large scope, and the Python interpreter at the time had this internal feature for maintainers that was supposed to be very clear in how it's implemented. It was supposed to be quite hackable and readable. We have to understand what we're dealing with, otherwise how can we maintain this interpreter? Jython, an implementation of Python in the JVM, famously does not have the global interpreter lock, so it is definitely a possibility, but what they also don't really have to deal with is all the extensions to your Python modules and libraries written in C. So because they don't really deal with the C API, it is easier for them to also drop the global interpreter lock and just have finer grained locking that is using some of those same facilities like already present in the JVM. In the meantime, in 2015, Larry Hastings did also successfully remove the GIL from Python 3.5. And again, he discovered that the result is very slow. Spending a lot of time like fine-tuning reference counting so that it could be deferred and so on and so on, he was able to meet the performance of a single core with his version, but he needed to use like 7 cores to match the single core performance of the regular Python interpreter, which 7-to-1 is a large ask for anybody. So at some point, he attempted, kind of actually making a new garbage collector for Python for Gilectomy 2.0, but very quickly it turned out that like this is an area of research that is so large that he couldn't just do it by himself. So, his work is very important. It identified reference counting as like a big scaling bottleneck. It showed that actually removing the GIL and replacing it with, finer grained locks is possible.
Right.
The performance is the make or break of that change.
And this is an interesting realization, right? Like a lot of people say, "Oh, removing the GIL is extremely hard, and that's why we have not done it yet." But the actual reality is that no, actually removing the GIL is very easy. You just add tiny logs on all the Python objects, and you're done. And the problem is making it fast enough, right? Like that's where the actual price is. Like you cannot just add logs to everything, because even in the single-threaded case, even if logs these days are extremely fast and efficient. And like I remember Larry mentioning after conference, like tons of people approaching him and saying, hey, look, there is this crazy implementation of logs that is super fast and blah, blah, blah. Like that doesn't matter. It's still slow, right? Like, because if you're doing it hundreds and millions of times, because reference counts happens a lot, then you're losing the battle. So you need some heavy weaponry here to make sure that you don't make Python twice as slow or something like that.
Right. Yeah. So I would like to qualify, like maybe like for Pablo Galindo, like removing the GIL is easy. Like for me in particular, it wouldn't be. So just that operation alone, even if you don't think about performance, is still a feat of engineering. Since if you're removing one lock and you replace it with 2,
well, conceptually it's easy.
Well, you're introducing a new class of problems that did not exist before, and that's deadlocking, which is the situation where you're holding a lock, waiting for some other resource, and that other resource actually holds another lock and waits for your first resource. And the two combined together will wait forever because, like the ordering of operations is simply invalid. So making sure that deadlocks don't happen is not maybe a trivial task, but it's definitely tenable. We can solve this. Like this is something that you can do, but the performance on top of the correctness here like makes it a real challenge.
Right. And this leads us, I think, to the 2021 approach, which is the first version of the current PEP, which is Sam Gross, who works at Meta. And he basically was working for a long time on a version of Python 3.9 that basically uses a bunch of like new approaches to this problem. But ideally, basically, the whole thing is that he removed the GIL by adding these locks and then he fought really hard to bring back performance by implementing a bunch of optimizations on top. So the idea is that you do the kind of a straightforward way with some new methods to make reference counting as fast as possible that we are going to discuss here.
Yeah.
But then the rest of the work that is here is trying to bring back that performance, like optimizing different ways and trying to use these locks the least amount of times possible.
Yes, exactly.
That was a proof of concept. He sent this email to our mailing list. Initially, people were a bit skeptical because like every time someone claims to remove the GIL and have like the same performance, you take it with a grain of salt. But some actually succeeded. He did the thing. It's just that the patch was ginormous, so it was very difficult to understand. Even if he actually, sent also, like, if I recall, a Google document describing the technical aspects of his work. So it was not just passing by with his car, dropping 6,000 line patch or 11,000, if I recall, and saying goodbye, I solved the thing, goodbye. He actually tried to explain how he did it and all that.
He spent like some considerable work to make sure that this is something that you can incrementally understand. So the nogil 3.9 branch was, I think, 74 commits, and they were structured in a way where everything just led to like commit 74 that actually disabled the global triple lock. But there were changes that came before that were more like, kind of preparations for this last one step. And, kind of over the course of every commit, you could still run the Python test suite and it would still be passing. So, kind of a lot of work there was put like so that the change did look incremental and you could actually kind of understand like at least, what one particular change was doing. But some of those single commits were still huge. Like when you're replacing, kind of reference counting with this non-eager reference counting version, like obviously this is going to be huge. And some of the changes that he made at the time, like were not even something that we're going to be, in fact, probably having like with PEP 704. Some of the changes there were, kind of needed to make performance look better, but we decided ever since that this is really something, like say orthogonal or something that doesn't really make, isn't really related to this one change. But yeah, he came to us, like, there was some interest, so we even ran like a meeting with him in late 2021. And it had to be online because, COVID and everything. I wrote like some summary of like that meeting, on the blog. We talked about whether this is feasible to implement or not. But, kind of there were tons of questions on, whether this is going to be good or bad for the community at large, whether this is going to break the C API, whether this is going to introduce subtle bugs that are impossible to debug now, and so on and so on. So deciding on whether we're adopting it or not was pretty much like impossible. Like nobody wanted to really be that person that says no, but also nobody was sure enough to say yes. So only in 2023 we arrived at a moment where this was formalized into a PEP to actually get this answer from the steering council, like, are we doing this or not?
Right. And in 2023, Sam created this PEP, which is the one that we are going to talk about here in detail. And he actually rebased, the whole implementation on top of 3.12. So we can actually check it on top of the latest improvements that we did in Python 3.11. And very recently, this past week, as the time we are recording this podcast, the steering council, we accepted this PEP with a bunch of conditions. So it's not just blank acceptance. There is a bunch of things. In particular, we are demanding that the rollout has to be gradual, and then we are going to break as little as possible, and then that we can potentially remove all the code if it turns to be impossible to maintain or people cannot adopt it or things like that. So there's a lot of caveats. Maybe we can discuss them at the end. But yes, this is affecting. This is something that is happening. It will take a lot of time. We are envisioning a multi-year plan here, so because we don't want to make the same mistakes as we did with Python 2.2.3. Totally different scenario, of course. We are not changing the syntax or anything. But we learn our lesson. We want to be as careful as possible to not break everyone. But yes, it's happening. So and ideally, we are going to we have read the document. I mean, I certainly have read it because I'm in the steering council and I have accepted this document. So it's good that I know what I'm talking about. But Łukasz as well has read the document in quite a lot of detail.
Right.
And we are here to discuss how it works, basically, or what is the idea. Let's start with the first thing, which is one of the core changes that is going to create more problems that the PEP tries to solve, which is bias reference counting, which sounds very scary, which is proper because we are close to Halloween, so we can say
bias reference counting.
Okay, so the idea here is that we have this number of reference that would tell us how many people are using a given object, and now we need to make this number work across multiple threads.
Right.
We cannot just leave the number as it is because, as you know, when threads are incrementing and decrementing the number without any form of locking, we can have races, right? And then two threads can read the same number at the same time, and when they decrement it, like we don't have -2, we have -1 or something like that, right? So we need some kind of locking around this number, which is very slow. So the first obvious stupid idea is to add a lock, even if this is your fastest lock possible. Unfortunately, every single attempt that we have tried at this, it has failed because it's too slow. The next idea that you may have is that modern processors have these atomic instructions.
Right.
So there's this idea of using atomic integers, and this is a way which you don't really require a lock, at least explicit. And the CPU performs this special memory ordering, in which case it ensures that if you increase from one thread and you decrease in order, this is kind of synchronized. Unfortunately, this is also very slow, among other things, because when this happens, the CPU needs to throw away caches and they need to synchronize across the different cores and a bunch of things that make the whole thing still very slow. So the idea is using these atomic increments and decrements is better, but it's still not the best, right?
Yeah.
So what bias reference counting says is the following: when you create an object, normally what will happen, or most of the time what will happen, is that the thread that creates the object is the one that is more heavily going to use it, right? It kind of makes sense, right? Like you can think how this may be true. Of course, it's not like we don't prove it. We cannot just, you can probably imagine a program that doesn't do this, but most of the time this is what's going to happen. And the idea is that then every object will have two reference counts. One of them will only be used for the thread that creates the object, and that is unsynchronized. That is only touched by that thread, right? So +1, -1, it works fast and nice. And then there is this second reference count field, which uses an atomic integer, right? And obviously we can change this implementation to something more funky, but for I think the actual implementation and for simplification of this, it uses one of these atomic increments and decrements. And the idea is that every single other thread will modify this second field, right? So we have like a fast version for the thread and a slow version for the other field. And the whole idea is that from time to time, the main thread will kind of fold this second number into the first one. So it will basically merge this other thread's reference count into the first one. And there is some logic to find out when we need to deallocate the object, right? Based on these two fields. But this way we ensure that most of the time when we do these operations with the main thread, they remain fast because there is no locking.
Right. So yeah, like most objects, in fact, like stay within the thread that they're being created in.
Right.
But even if not, and we're using the two fields, like the thread that created the object is the owner thread. So that is the thread that actually will now decide that, okay, the reference count really reached 0. So now it's safe for us to deallocate the object.
Right. And then the idea is that we mark basically the states of objects to account for like changes that happen to them to, make some operations faster if we don't need to do heavy things. For instance, if no other thread has ever touched the second field, then we can just remove the object as we do normally on CPython.
Mm-hmm.
So we have these different states and we use like a bit of a hack. So in the reference count, this is a big number. If you look at this number in binary, we use the least two significant bits of the, number in binary to mark the state of the object. And basically the object can be in 4 states. One of them is basically the default, which is like, the normal Python object, nothing has touched it. But as soon as like other threads start to access the object, or like you start to support certain operations like with reference and things like that, we move these status to other ones. Like particularly right now we have 3 more. One of them is called weak refs that says that the object starts supporting weak references and other operations that are optimized, like is in some list or dictionary or things like that. And at that point, then it needs a bit more careful consideration when you want to destroy this object. So when you have an object in this fashion and then you start operating on them, it can transition to this status that we call queue. And this status basically it means that some other thread has started modifying this object, and it requires the main thread to kind of fold the number into the first one to figure out if it needs to be deallocated or not. And then the last state is when the fold has happened, which we call a merge. Because you merge these two fields together, and then the main thread or the thread that is basically in charge of destroying this object, it has to do the logic to figure out if it can be destroyed right now or need to be deferred to GC or something.
Right, and frustratingly, all this is still making reference counting too slow. So there's even more changes that we need to make to actually make it not too big of a cost to change this reference counting to be thread safe. One realization that we have is that there are some objects that are just accessible for the entire life cycle of the interpreter. Once you start it, the object is going to be created and it's never going to be deallocated until you shut down the entire process. Examples of that would be false, true, none. This is already kind of simplified and allowed, making it faster with PEP 683, which allows for object immortalization. So essentially, this object doesn't have to be, present in all the garbage collections that are happening because it's never going to be deallocated. So there are some small changes that we need to make so that it also works with biased reference counting. And that is still not enough because there are objects that are not quite immortal, but they're accessed super often in a Python program. So those are usually some of the objects that are globally accessible, right? Like top-level functions, you have code objects, you have modules. Those don't use immortalization, right? Because they, kind of in theory, you can remove a module from sysmodules, right, or you can replace a top-level function with another one, and so on and so on. So they aren't always kept for the lifetime of the program, but usually they are kind of global state. They are very often accessed. So what we do with those, we also defer their reference counting. So we can say that one of those two most significant bits that we treat specially in a reference counting, in a reference count, is used to mark this object as deferred reference counting. And that counting only happens during garbage collection cycles, which are way less done way less often than regular reference counting, which is eager, right? It happens, every time you leave a scope, right? Every time like an encref or decref is happening. So for different reference counts, that's not true. We will only try to calculate the number of the reference counts during GC cycles, but that makes this operation happen way less often, making everything faster.
Right. This still requires some changes on the whole GC because right now it means that, what we are trying to avoid is every time you, let's say, push one of these objects that are accessible from the global state to the Python stack. So for instance, in a local variable somewhere or accessible from a local variable, you cannot don't do these operations, which means that when the GC is trying to find these objects, we need to teach the GC also to walk the Python stack as well, all the thread stacks to figure out also like, okay, so these reference counts are delayed, so you need to account for them to figure out that indeed you need to destroy this object because right now the GC doesn't understand how to do that. Mm-hmm. So like more changes are pushed to the GC to ensure that Python, the GC understands this new concept of delayed reference counting.
Right, and also the garbage collector now will have to be able to visit all the threads, right, to actually kind of follow the stacks everywhere so that it knows what actually still stays in memory and what is not.
Turns out that this doesn't solve all the problems. This only solves the reference problem, the reference count problem, right? So now, with this method, we have a way to, refer to objects from different threads in an efficient way, or at least more efficient way. But you still have a lot of like synchronization problems. Like if you have two threads pushing elements into a list, so calling list.append, this can still race, right? So now it turns out that we require a lot more changes to ensure that your Python application doesn't crash. And this is kind of important because like in a compile language, if you allow me to say a YOLO language like C++, when, it's up to you and it's free lunch, there is no, a nice borrow checker or compiler, yelling at you if you don't do it correctly. but performance. Then the problem is that if you have, let's say, a container like a vector, and then you're trying to push from two different threads to that container, or maybe remove at the same time, your container can end in a really bad state because access is not synchronized. So you need to protect this with a lock. And the problem is that if you don't do it, it will crash.
Yeah.
Technically, it enters this realm that is called undefined behavior, where unicorns can appear and according to the holy standard. But in practice, it basically will crash in a weird way, and it's going to be very, very hard to debug. And in Python, we don't like this. Like, we don't want our programs to crash just because you're not using locks when you're appending to a list, right?
Yeah.
Maybe we want to show you at least a nice exception, or in the best case, we want it to just work, because right now that's the way it is. Right now, if you append to a list from two threads, it's working. You can still have some surprises. Like, for instance, if you use list.remove with an index, and then for another thread you append to it, you may remove the wrong element if these two race, because the GIL can be switched.
Exactly.
But it won't crash, and you will not end with like the list thinking that it has 10 elements but really has 9. So when it tries to remove it, it just crashes. So we needed a bunch of changes, and these changes are supported by basically coupling a bit more the way CPython manage memory, because as you will see, this uses some of these tricks by controlling the memory allocator to basically add some information when we allocate objects. And this is achieved moving CPython to a new memory allocator called mimalloc.
Yeah, exactly. Like, if the amount of detail so far was already high, like, no, we have to go deeper.
We have to go deeper.
Before we deallocate things with reference counts getting to 0, or with garbage collection deciding this object is no longer reachable, like, we have to allocate the memory for a particular kind of object. Maybe it's a dictionary, maybe it's just some particular integer or whatever else. So for now, Python is using PyMalloc, some wrapper on top of more low-level allocators that you have on your operating system. And in fact, it's pluggable, so you can have an allocator that will help you debug things and so on and so on. But the core feature of PyMalloc that allows us to be relatively efficient with different sizes of objects we have and so on, is that it is not internally thread safe. It doesn't have to be. And the reason why is that we have the global interpreter lock, so we can just use that one to make sure all the allocations are still correct. So now with the GIL removed, we would be back in the game of making PyMalloc thread safe, and more important, to still maintain its performance. And it turns out it would be actually easier to swap out PyMalloc as we understand it right now with an allocator that is internally thread safe. And mimalloc is one such allocator.
Right. I think the me in mimalloc stands for Microsoft. This is a Microsoft project.
I think so, yeah.
And the idea is that not only this is a thread safe allocator that is very fast and very efficient, it also happens to have a bunch of features that we need for ensuring that all these operations that need synchronization, like appending to lists and things like that, stay fast. And the idea here is that, for instance, mimalloc allows us to have basically private heaps. So the idea is that when you call right now PyMalloc or even malloc, it will return you just a bunch of memory. So it will give you a pointer that points to a region of memory, but that can be anywhere. Like, it can be, the pointer can have any value. It can be in any point of memory. You have no control over that. But the idea is that when you have these private heaps, you have this kind of like areas of memory when you can allocate some objects there, right? So basically there is functionality in mimalloc to say, I want my pointers, for instance, for dictionaries only in this particular area. And then you can ask back mimalloc, tell me, okay, allow me to, iterate over all my pointers that are dictionaries, right? It can also be by range, right? You know that dictionaries are between this memory position and these other memory positions. So now, just by looking up the address of the object, or just by asking mimalloc, you can know if a pointer belongs to some region or some other. And this allows you to do some tricks with memory, and this is what we call segmentation, because you basically put objects that you care about together in a region that is different from the others. So you can start asking questions and only iterate over the ones that you want. And this turns out that is going to be very important for the changes that we require.
Yeah, so the important feature there is that now you can use private heaps so that okay, those objects that we're looking at are garbage collected. So we can actually now follow the garbage collected tracked objects without having to maintain a linked list as we're doing right now, which this linked list has a very confusing effect to, kind of casual users of Python, where ironically, even reading an object will sometimes write to memory. That is making kind of cache locality worse and so on and so on. So we can now maybe solve this issue as well with mimalloc. But most importantly, this is simply faster and this is, thread safe.
Right. Now that you talk about the GC, this also requires some changes on the GC for dealing with the whole thing.
Right.
As we mentioned, one of the changes that we need in the GC is that the GC needs now to be aware of the Python stack because we are using this deferred reference counting. So the GC needs to find out that the stack owns a bunch of these references that has not been done yet.
Right.
But it needs a bunch of other changes. One of the reasons is right now the GC kind of works because when the GC runs, it holds the global interpreter lock, so it knows that all of the other threads cannot do anything. So it knows that all the reference counts are basically frozen,
right.
So it can reason about them. And actually, the algorithm that it uses, that you can read about it in the Python dev guide, I wrote this document about how the whole GC works. But the idea is that it uses these reference counts to figure out where the cycles are. When the moment when you don't have the GIL anymore, it means that we don't want the GC to be running at the same time someone else is modifying these reference counts, because then the algorithm doesn't work. Which means that we still need to stop every single thread. And this model is called stop the world GC, when you basically stop the world,
yes.
Which is basically what we're doing right now, except that in the case when you don't have the GIL, you need to explicitly say no. Like now, when the GC runs, only one thread can reason about the reference counts. And this provides also a nice synchronization moment to, start to solve all this small deferred stuff. Like when you say, oh, let's do this operation later because, right now it's too slow to do it all the time. So let's put it here and let's do it later. So the GC run is one of the moments when you can start figuring out all these things that you left because all the threads are stopped. So it's this nice synchronization
right. So to be
moment.
clear, this garbage collector, this stop the world collection is going to happen only on a single thread, right? There's going to be one thread that is responsible for garbage collection.
Right. And some changes are made. One of them is that right now we have this idea of generational garbage collector. We have different generations for the objects, and
yes.
Objects in older generations are collected less. So one of the changes that this PEP makes is that it reduces the number of generations to one. The idea here is that it's basically much easier to reason about here, and you don't need to collect all the single time. So it's a matter of it's a balance of performance and implementation correctness. Just because the way the GC now runs over all the objects is not by traversing the linked list, but asking mimalloc for all the, traversing the memory raw, let's say.
Right.
And this not only, is simpler to do once you have this memory allocator cooperating with you, but also is much faster. One of the reasons is because when you are traversing a linked list, you are referencing a pointer every single time you ask for the next object. And, we have these caches in CPUs that make that traversing memory that is contiguous is extremely fast, and traversing a linked list is the opposite of that, right?
Yes.
But when we have all the objects kind of at least when you are scanning contiguous memory of the heap, even if you don't have, even if you have holes, right? You can just skip over them, but you have the entire cat lines filled, so you can just keep running in a very efficient way over that. So
exactly right.
We have now one generation, and when you ask for something like GC get reference or GC get objects and all of those APIs in the GC that allows you to get all the objects in the GC, we manually reconstruct the linked list for you because all these APIs kind of need to work with linked list. So there is some reconstruction needed in the middle that right now is a bit inefficient. But we can optimize in the future.
So the interesting thing is all the threads need to know that, okay, now there's this stop the world operation, there's a pause, we're doing the garbage collection. So what is the moment in which the threads actually synchronize and stop, and how do we do this? So it turns out Python already has a mechanism to stop execution in the current thread because another one requested the GIL. That mechanism is called the eval breaker, and we could just reuse it to make a global garbage collection cycle happen.
Right. Actually, one of the things that we have changed in Python 3.12 is precisely that this change, actually 3.11 I think also has a change, is that the GC only runs on this eval breaker, because before the GC could run every single time you allocate an object or you deallocate objects.
Right.
Which is kind of cool because, it has a lot of opportunities to execute. But on the other hand, it's very surprising because you may be, in the middle of preparing your nice object, maybe it has 3 other things inside. And in the middle of your preparation of the object, then the GC runs and then it does these all the crazy things, it deallocates things around. So what can happen is that it touches your object mid-allocation. And there is ways to prevent this, but it's really hard to, get it right just because, the GC can run at any point. And the GC is very scary because, it can execute arbitrary Python code when you call the destructors of objects or the finalizers of objects. So one of the changes we did, which is unrelated to this work, but is also used by this, is that the GC only runs on the eval breaker, which is more predictable.
And thanks to this, now that all the threads are stopped, right, and we know that they're not executing any code, like since the eval breaker is like very kind of elegant as a moment to do this, we can now traverse all the thread stacks,
right?
And through this, we can actually calculate, like the cycle references and do the deferred reference counts that some of the very popular objects mark themselves as being, and we can merge the ref counts from biased reference counting, right? Like so those 2 ref count fields from the owner thread and all the other threads to combine it and actually figure out like, is this object ready to be freed or not?
Right. One clarification as well is that when we say that it's a stop the world GC, this stop the world only is applied to when we are figuring out what objects are reachable and which objects are not. Once we know, which objects need to be destroyed, the actual destruction themselves is not frozen. Like all the threads can run at the same time the destruction happens. One of the reasons here is to avoid deadlocks. Like if you think about this quite a lot, it turns out that you can have different deadlocks if threads are still waiting for the GC to happen, and then you hit one of these finalizers that is waiting for some operation to finish. Then basically you are not advancing. So this means that when you start destroying objects, you need to allow other threads to continue. Otherwise, you can have deadlocks that you right now don't have. So it's not the end of the world, and this also makes the destruction phase faster because the other work can continue meanwhile we destroy objects.
Yeah.
Which also make it very tricky because many things can go wrong in this phase. But it's not as low as a huge stop the world that it waits for everything to be destroyed before continuing.
Yeah, the ordering of the destructions might be a little kind of non-obvious, but we know that when the objects are now like ready to be freed, that doesn't have to stop the entire rest of the program from execution, meaning it's faster. So kind of it combines this a nice intersection of correctness, avoiding the deadlocks if you have like Dunderdale, like some particular complex deallocation,
right,
and speed. So that's maybe a good segue to talk about the performance of collections and how we need to make those thread safe as well now.
Right. This is actually when things start. If you think this was already very complicated, just wait until you hear about this section because this is just bananas. So the idea here is that we have protected reference count using these like smart ideas, but now you still have problems. Like for instance, as we mentioned, we go back to the problem when you are appending to the list at the same time you remove from the list, or 2 threads are, one is removing keys from a dictionary, the other is accessing the dictionary. So what's going to happen there, right? Turns out that the solution is to just add a ton of locks to everything, and there is no other solution because when you access these objects, you need synchronization. So you need to ensure that only one thread can access these objects, just to ensure that the status internal is correct, and that's it. And unfortunately, as you can imagine, adding tons of tiny locks to everything, even if the locks themselves are really fast, is really slow. And the whole section of how the PEP talks about this is just to avoid maybe locking because again it's a very slow operation in some cases. And basically is the balance here is you trade speed, so that's what you gain by adding a huge amount of complexity to the code. So that's the you have heard about the balance between speed and memory. Wait until you hear about the balance between maintaining maintenance, complexity, and speed, right? That's the other side of the coin.
So to be clear, like we're talking about the internal code of the interpreter, right? Where the additional complexity that we're creating is partially just necessary for correctness, but partially also necessary for kind of predictability with what people understand as Python, like as is right now. So as Pablo already mentioned, there are a bunch of operations that could feasibly just return exceptions when some operation fails to be completed in a parallel way because there was some race with something else. But we don't want to change how people program Python. It would be very disruptive if things that used to actually succeed like stop succeeding. It is already pretty annoying to Python users, right? For user code to have to deal with containers changing size during iteration and whatever. So like if we had like another new class of exceptions risen in this sort of situation, it would for sure be unpopular. So in the end, we actually have to have new locks, and some of the time, like the number of new necessary locks is pretty high. Like there's very popular operations in Python when you're kind of converting one container into another, like having a list of sets and whatnot. So now we're gonna have to lock both of those, and that obviously creates opportunity for deadlocking when there's more than one lock, and so on and so on. So this is something that maintainers of CPython are not entirely excited about, because this is a new class of complexity that we didn't have to deal with before.
Right. There is some operations that they don't require the full locking mechanisms, which again is the slowest version of synchronization. For instance, if you are asking for how big is a list, like the length of a list, you don't require locking because that is only reading an integer that is kept by the list. So as long as operations that append and remove are synchronized, reading this you just need an atomic read, so which is a bit faster, but still not as fast as just reading a regular integer. But in general, like you require locking even for, as Łukasz mentioned, several containers at the same time. So basically what the PEP tries to do is to introduce these like optimizations up top, leveraging the fact that we control the memory allocator to avoid locking in some of the cases. And the cases that we're going to try to avoid locking is precisely the cases that are more common in Python. For instance, accessing dictionary objects, right? When you have a dictionary and then you have a key and you access the key. So basically you get an item from the dictionary. This needs to be fast because otherwise Python is going to be very, very slow. And the same for other things like, getting elements from lists, like calling next on iterators and checking if some element is in a container. All of these things happen all the time. And then there is these tricks that the PEP tries to do to avoid using the heavily locked machinery to lock around these objects and do it.
Avoiding locking is not something that is generally possible every time, but there are algorithms that are known like for us to be able to avoid a lock in a particular well understood case. And we have a bunch of those. There is a lot of operations that have like a very predictable happy case and complex edge cases. So now we're going to be splitting implementation of those operations into this fast path that like will not employ locking. But if we identify that we are reaching an edge case, we're going to go into this full correct but slow path.
Right. Like for instance, one of the changes that this does is based on what is called RCU, which stands for read copy update semantics, which is a trick that is used by the Linux kernel to do a scalable, access to unsynchronized containers, which is a bit complicated. But the idea here is that, for instance, if you're accessing an element of a list, there is two main operations that you need to do. One of them is, increasing the reference count of the whole thing, and then you need to fetch the element. And these two operations are not atomic, which means that something can happen in the middle. For instance, something can destroy the list before you access the element, or something can add a new element to the list. So the one that you were trying to access is in a different place because someone has moved the buffer, right? Because when you add elements to a list, it may be in the same buffer, but sometimes when the list is full and needs to reallocate, it moves the buffer somewhere else. So the pointer that you have right now is not the one that you used to have. So the idea here is that there is a bunch of, like, if you listen to this, it's going to sound a bit hocus pocus. So you need to kind of sit down and think about it and read a lot about this. So don't just trust us for what we're going to see. But the idea here is that you have a really fast path that basically what it does is that it does a bunch of atomic operations. So basically it atomically loads the list buffer, for instance, and then you atomically load the element in the buffer. So basically you get first the internal array that holds the Python object in the list atomically, and then you atomically also get the element inside the array. And it turns out that is not enough because some of these operations may fail. In trying to increment the reference of the object can also fail. And then there is also like some other threads can do things in the middle of these two operations because even if each one is atomic, both of them are not atomic as a whole. So you need to do a bunch of checks after that. So for instance, you need to check if one of these operations fails, or like you need to check again if the item that you got is is still there. So you get it again, and then you check that indeed the item that you got is still there. And you also need to check that the buffer is still the same buffer and nothing has appended to the list and changed the buffer. And if all of these things are true, then you don't need to lock. You just pay 2 atomic fetches, and that's kind of nicer than you don't need to lock. But if one of these fails, then you need to go back to the slow path that uses the entire lock and ask for the whole thing. This actual trick works because if you think about it enough, or you pretend that you understand what I just said, this is not enough because some of the things can happen in the middle, specifically when some objects are destroyed. In particular, you may be reading for free memory, and that is still obviously not good because reading for free memory is undefined behavior. And what happens is that this actually works just because we control the allocator, and we have modified mimalloc to do a bunch of things that allow us for these operations to make sense in a way, right? So even if the memory may be freed, you can still read some of these values, particularly reference count, from memory, and those will be valid.
Yeah, mimalloc uses pages that are blocks of the same size. So even if that is freed memory, okay, yes, that object is no longer valid, but you at least know that the structure of the object, that the bytes will still make sense. That you're not going to have like kind of fields that you read as say reference count, and it's suddenly like entirely different data. Meaning like those, for example, special bits that we talked about would be like insane values, right? So you can still kind of read this outdated memory, right? Because it's no longer current, but at least it is not entirely different information. I mean, it might be, but only in the case where there are no blocks allocated within the entire page. Then mimalloc can say, okay, like this entire page can be reused for something entirely different.
Right, and this is like the whole key. Like the idea is that we have some modifications on top of mimalloc that avoids mimalloc reusing these pages for something else. Because obviously, if you start writing to these pages after the object is deallocated, you may end with a totally different thing when you read to it, and you don't want that. You still want to ensure that whatever you read is either the reference count that you have or 0, right?
Exactly.
So you have like control over what can happen. This means that we need to basically lock without an actual lock, right? This is just lock as the English word, not the data structure. We need to lock the page and say, as long as we are trying to still read from this page, mimalloc cannot touch this. It cannot just return the page back to the system or to the allocator to reuse it for something else. And this is kind of nice because, this trick works, and then we can have this fast access, which is also working because, we don't lock random pages. We use this trick that we mentioned before of segmenting memory in different heaps, as mimalloc calls them, to ensure that, dictionaries go with dictionaries and GC objects go with GC objects and whatnot. So this allows us to efficiently be able to lock these pages for, not reused by mimalloc. But this leaves the problem that when we unlock these pages, right? Because, okay, so you say, don't touch this page because we need to read it still. But at some point we need to say, okay, this page can again be used, because otherwise you need to lock an entire page of mimalloc every single time you do these operations, which may have a huge impact on memory, and we don't want that. And by the way, one clarification here: when we talk about mimalloc pages, this is not the operative system pages, right? So this is not 4K regions of space. It's just an internal mimalloc structure that can have different sizes and whatnot. So it's not like when we say pages, you don't think about this 4K regions. Do you think about like some internal data structure that mimalloc
Yeah,
has?
it's like a subset of one of those heaps that we were talking about, like inside inside mimalloc. So like heap the heap in general is not accessible with the regular malloc. Like you can kind of not decide where you want the memory to come from. You're just getting a pointer back. With mimalloc, we have heap segmentation, so we can actually decide like kind of, oh, this is a object that is garbage collected, so it should live somewhere else than other objects, so that we can be faster at kind of actually following all this garbage collection information when we're doing the stop the world collection. So how many heaps do we actually have now?
So I think we have mainly 3 heaps plus some specific like internal ones, but the main 3 heaps are like all the objects that don't participate in GC go into its own like bucket of memory.
Yeah.
Then we have 2 heaps for the GC objects, and this is just because there is this concept of managed dicts. The idea here is that if you have a normal Python class, Python knows how to manage the internal dictionary. And we actually have these optimizations that Mark Shannon did with Inadasan that basically don't create the dictionary if it's not needed. And this is quite cool because like most of the time when you are accessing an object, having to use a dictionary access and hash the thing and all of these things is quite slow and it uses more memory. Because most of the time you are not looking at the actual dictionary of the class, which is normally accessible in object under dict. So we have these operations internally that speed up access. But C extensions can still use like internal layouts of the classes and use the fact that there is a dictionary there and access the dictionary as a dictionary. And also users can also do like dot under dict, in which case we need to create the dictionary for them if it's not there, and C extension can still use a dictionary normally. So for those C extensions and other cases, Python uses this idea of managed dicts, which basically says, okay, so I'm not managing the dictionary internally, so I cannot do all these fancy tricks. You do it. And for those, it turns out that, for internal details about how these GC objects work and, what we can and cannot do, they go into their own heap. So basically we have 3 heaps: non-GC, GC with managed dicts, GC without managed dicts. So that's the main segmentation that we have.
Right. Yeah. So like potentially, if you have this change to mimalloc where we still want to look at reference counts of objects even though they're already deallocated, and that keeps the entire page potentially still in memory. Like in a very unlucky scenario, you can have a lot of those pages alive, meaning the memory use of Python is going to be way higher than it should have been, right? So like, we have to have some way to alleviate with that problem so that we don't have to wait until the next garbage collection cycle to reclaim this memory. Otherwise, we could just be killed by our hypervisor, like when the container is suddenly, requesting too much memory. Or within Linux, you would have like this killer, kill your process before you have a chance to actually clean up after yourself. So what do we do to actually make this less of an issue?
Right. This is when the whole thing starts becoming even more complicated. So the idea to basically get rid of these pages that are locked and just to make the container access and synchronize, well, not synchronized, but without locks a bit faster. It uses an approach that is used by the FreeBSD operative system called global unbounded sequences. We were like looking at this, and explaining this thing in a podcast is probably like too complicated. I will give you an idea of how it works, but this uses the word counter 4 times in different ways. So it's just the 3rd time I'm going to say counter, your head is going to explode. Like mine did. So, but the idea here is that to ensure that we know when these pages need to be can be reclaimed and reused again because we are not locking them. Basically, there is like a bunch of counters which acts as like generations, and basically there is like a write counter and a read counter, and every thread basically keeps track of the last counter it has seen. And every time we lock one of these pages in these faster atomic operations. Well, not atomic operations, but the container operations, we mark that page with one of these counters. And then there is some logic that every thread uses to look at the counter in the page and the counter that it has seen. And there is some conditions when it knows that it's safe to actually, unlock the page, because it knows that on those conditions, nobody actually, is going to read at that page, and it can be actually reused, right? Like the condition can actually be checked just by comparing these numbers, but you also need the logic to keep these numbers up to date and, increase the global counter and whatnot.
Well, like if the GIL is being controversial for a group of Python core devs, one group that was especially worried was the faster CPython team, because the specialized interpreter that they were working on relied on the global interpreter lock to make sure that the specializations as they are happening were still produced in the right moment, and nobody else could actually come in the middle of the specialization and break everything. So now there's some changes in the specialized interpreter that are required to live in a world where there is no GIL anymore. So for example, like we have specializations and they can only actually happen for a piece of bytecode once. But more importantly, we have a mutex now that when the specializations would be happening, but the mutex is actually held, like we avoid multiple threads writing to the inline cache at the same time. This is obviously something that has impact on specialization performance, because that mutex didn't exist before. But the locking does ensure we have this consistently cached, right? So like the two tags that we keep, like they're consistent with one another. So yeah, this is essentially making the work of the faster Python team more complicated to still achieve specialization, but to make sure that you can run multiple threads now actually in parallel.
Right, and this is actually interesting aspect of this, because this was adapted to 3.12, because when Sam did the first version, there was not an adaptive interpreter, so the first version of this work didn't have to deal with this particular version. And now, the PEP was modified after this to account for this. So this is an area that, we can improve over time, and we don't need to be as aggressive and as, cautious regarding these optimizations. Also, as said by the faster CPython team, this is a new realm, right? Because normally what you get in the literature is that you get all these papers and strategies when you have some form of locking or you have free threading. But having an adaptive interpreter in the presence of free threading is kind of a new thing, or at least there is not as much research into that, which means that there is less known approaches that you can do in this case. So the whole thing becomes a bit more complicated, because now you're dealing with two very complicated aspects, and it becomes even more complicated if you have a just-in-time compiler in the mix, because the just-in-time compiler can need to generate this native code, and it needs to do this thing in a kind of synchronized way, so two threads don't generate different kind of code just because one thread is using one function for floats and the other thread is using the same function for integers. So those kind of optimizations need to happen in some coordinated way, which makes the whole thing a bit more difficult, because now both approaches need to know about each other, which means that it's going to be very important moving forward that everyone talks to everyone in the core team, right? Because you cannot just do the nogil stuff in one way and try to optimize Python to make it faster in the other way. Now both everyone needs to talk with everyone, just to ensure that we keep ourselves synchronized, so we don't race with each other in the changes that we do to CPython.
Right, and this brings us back to the terms of acceptance of PEP 703. Obviously, there are still many details about how nogil works. We could talk about how the CAPI has this concept of borrowed references and how they're actually making everything way harder to reason about with the presence of free threading. We could talk about the method resolution order that is used to figure out which particular method version in a class that has an inheritance hierarchy should be used, and how that needs to be sped up with the presence of free threading while still maintaining correctness. So there's many other details that are interesting, but we reached the hour on the episode right now. So maybe let's actually go more high level once more and just talk about what the acceptance of the PEP 703 really means, right? Because what I think actually helped the steering council make the decision to accept this change to be made was this reframing of the problem from let's remove the GIL, let's just go and make this huge change, into let's make it possible for users to build a version of Python that does not include the GIL. That way, we can allow the users to experiment with the resulting interpreter, produce free threading versions of NumPy, SciPy, and so on, so that you can actually see whether this helps with scalability, whether this helps or hurts performance in the real world, and more importantly, does it introduce this new scary class of free threading errors that, like, so far we didn't really have in Python. Well, we did have them to some extent, but since threading was so crippled, it was relatively little used, right? So now there's a whole new world. Everybody wants to have answers to those questions, like, is this going to be awesome or terrible? And we cannot really, use any clairvoyance here. We really just need to test this. So what PEP 703 says is, let's allow the configure script to have an option where we're building without the global interpreter lock. But that is not entirely compatible with the version of Python that was built with the GIL. Or actually, now we're going to have to think about the changes made for no-GIL all the time, even if we're using the version with the global interpreter lock. So what's going to happen to the C API?
Yeah, that's actually something that is very important to remark here, because a lot of people think like, oh, the CPython team is removing the GIL, so it's going to be free lunch. And actually, due to these things that Łukasz is mentioning, this is going to be challenging for a lot of people. This means that, maybe if you have pure Python code, you don't need to think that much about it, especially if, you have proper synchronization already in the presence of Python threads. But like C extensions will need to think a lot about this, because as Łukasz mentioned at the beginning of the podcast, right now C extensions can be really happy because they know that only one thread can manage their objects at the same time. But this is not true anymore, which means that now you need locking almost everywhere or some other strategy, or at least you need to think about it. And the problem is that thinking about these multi-threaded problems is not too easy, because even if there are some tools like thread sanitizer and Hillgrind and things like that, there is nothing that will tell you, you have a problem here and you need to put a lock here, unfortunately, right? And even less in the presence of all these tricks that we are doing. So this means that, one of the reasons we are doing this thing very slowly is for understanding how challenging it is for C extensions to be compatible with no-GIL, and try to see if this is actually something that the community wants to pay, because the community will pay some things, right? For instance, as Łukasz was asking, like what happened with the C API? Well, this means that no-GIL needs an entire different C API. Maybe it's not a huge area of like functions that are changing, parameters and names and things like that, but they need that some APIs that we offer are not valid anymore with no-GIL, and on turn you need to change the semantic of some other APIs. For instance, the APIs that acquire the GIL and release the GIL, obviously they're not valid anymore if there is no GIL, and so they need to do something slightly different. Also, like all these borrow and reference need to go, which means that there is a bunch of things that will change, and this means that the community needs to pay this price in many ways. One of the ways is that now if you provide wheels, these are pre-compiled versions of your packages for C extensions like NumPy or SciPy or things like that, you need to provide one wheel also for the no-GIL version, which means that you need to build twice as many versions of Python, assuming that all the versions can be no-GIL and GIL, but also you need to test them. So you need to test with GIL and with no-GIL and build these two things, which means that the CI will take twice as much time unless you do it everything in parallel. But that's for sure you will consume twice as many resources, assuming that you have both versions, right? Obviously, T13 is the first version that may have this, and assuming that you want to opt in, because this is not going to be the default for a long time, you can defer doing this in the future. But if you want to try, it's a bunch of work that you need to opt in. And in the steering council, we have also discussed, and it's in the acceptance notice. So we wrote this super long text that I invite you to read in the Discord Python webpage, when we basically list all the conditions that we require for going forward with this change. And one of the things that we mentioned is precisely this idea of having two C APIs, and how we may not want to have this thing when we move phases. So people don't need to build two versions of the same thing, and we only have once. So this is a tricky thing, because obviously this means that when we merge both C APIs, let's say, into the same one, it means that all wheels won't work for the new thing, because it's a new entire binary tag and whatnot. But it means that, moving forward, people won't need to create these two different things for everything, right? So there is a lot of aspects that are very complicated, and especially regarding the C API. So there is changes that are required. There is semantic changes that you need to do. There is a lot of thinking that you need to do. You want to ensure that your C extension works with nogil. Sometimes it's going to be very easy. Other times, especially if your C library is very big, it's going to be very challenging. Maybe doing this in languages that are a bit more careful with threaded, like Rust, may be a bit easier. But a lot of time you still need to do a lot of work, because normally all these interactions with the C API happen in unsafe code in Rust, so you still can have like weird things happening there that the borrow checker is not going to protect you against. And then you have all these bugs that Łukasz was mentioning on top of that, right? Because if you when you're doing these changes, you do them incorrectly, you may run into deadlocks, you may run into live locks, you may run into crashes, and which are also very hard to debug, because when you are doing this deferred reference counting, it means that when the bug is seen, it already happened long ago. It's just when when the thread merges the reference counting, now it's bad. So you need to use this super advanced debugger like RR, the reverse debugger, just to understand what happened going backwards. So it's going to be an interesting time. I don't want to scare people. We are close to Halloween, as we said before. This doesn't mean that it's impossible. It's just that we need to take this thing as a community in mind, because many people are looking at the change and it's like, oh, nice, we finally have it. Well, yes, and all this pain as well, right? It comes in the same package.
Yeah.
It's important.
It's definitely a radical change. One kind of reason why it was a good time for this, or maybe if it wasn't the best time, it was the only time, was that we did have Sam Gross's like no-GIL branch that was a proof of concept of this actually being successfully implemented and performant enough for us to consider. And we might not get there in the future again, right? If we don't attempt removing the GIL right now, with the heavy changes that are made for the specialized interpreter, for the just-in-time compiler, and so on and so on. This kind of experiment with removing the GIL interpreter lock becomes harder and harder to execute. So having this branch that already shows us, okay, this is feasible, this is already done, is something that we really need to kind of take into account. Since we cannot just leave the branch there for a year or two, it would become stale, it would become unusable for us. Hence, even though there is so much change in terms of performance on the Microsoft Steam end, we actually didn't have much other choice than to start the no-GIL experiment at the very same time. That requires a lot of coordination. This will require a lot of work, but there is plenty of opportunity for this to be the most kind of radical improvement in the quality of the interpreter that we've seen in decades. So there is plenty of opportunity for Python to reclaim its position in this orchestrating language, where it stops being the bottleneck for not even executing its own kind of pure Python code, but for executing other code on CPUs and increasingly on GPUs, where they can be fast enough that even orchestration from Python now is affecting what you can do compared to running it without the interpreter. So yeah, hopefully we're going to be feasible, and we're going to be still kind of considered modern technology into the future. If we build 3.13 with no GIL and the users find that, okay, maybe there's issues, but they're worth it because the compromise of allowing scalability is converting this language into something much more powerful.
Right. Maybe something that we can do in the future is to actually bring Sam Gross himself here to just tell us everything that we said that is incorrect. So, every mistake that we have made, just reach to us if this is something that you would like to hear in the podcast.
Right. Or if we did go a little too deep or maybe not enough, just let us know what we can improve such that the level of the detail is what you're expecting in the future. This was a very exciting episode to do because the PEP was just accepted officially. So now the real work can begin with the continuous integration, actually building nogil on our end with new build bots, with the entire team actually having to now read up on PEP 703 and how to make their change thread safe from now on. There's still a lot of unknowns even on our end, like what is the extent to which we're going to have to adopt the Stein library, a lot of which being just pure Python, but a lot of it is marked explicitly as not thread safe. What are we going to do with that? Are we going to adopt all the async.io APIs that don't claim thread safety, or are we going to leave them and make the users worry about that, and so on and so on? So there are still like a lot of challenges.
Yeah.
Like, let's call them challenges, not problems.
Wow, talking like a manager, eh? So this is everything that we have for you, at least in hour and something like 10 minutes that we are ready. So we hope that you enjoy it, and we hope to see you in the next episode.
Yeah, see you.